Hello friends, here in this video we will see how many types of gas power cycles are there for an IC engine. Gas power cycles for IC engines. Now, here I'll mention how many types of gas power cycles are there one by one. The types of gas power cycles in IC engines are: the first type of cycle, it is Carnot cycle. Second, Otto cycle. Third, diesel cycle. Fourth, dual cycle. And fifth, Breton cycle. So these 5 cycles are there in case of gas power cycles. Now I'll start explaining them one by one, that is starting with the Carnot cycle first. Carnot cycle, out of all the cycles which we have, Carnot cycle will give us the maximum efficiency. So it is a reversible cycle which gives maximum efficiency when compared with other types of cycles. So Carnot cycle, it is a reversible cycle which will give maximum efficiency when compared with the other types of gas power cycles. Next, in this cycle, all the processes are reversible. In case of Carnot cycle, the processes are reversible, and here I'll mention the processes. The processes which take place in Carnot cycle are, there are basically 4 processes. So starting with the first one, process 1 to 2, that is it will go from state 1 to state 2. So process 1 to 2 is reversible adiabatic. Reversible adiabatic is also called as isentropic compression. That is the process 1 to 2 having reversible adiabatic. The other name is isentropic compression. Second, process 2 to 3, it is reversible isothermal heat addition. Then process 3 to 4, it is reversible adiabatic, which is again isentropic expansion. After compression, heat addition, there will be expansion. Then at last, during process 4 to 1, there will be reversible isothermal heat rejection. So here I have mentioned the processes which take place in Carnot cycle, and as we can see, all the processes are reversible, and it consists of isentropic compression, isentropic expansion, then isothermal heat addition and isothermal heat rejection. So we can even simplify Carnot cycle that it is made up of reversible adiabatic processes, that is isentropic, and reversible isothermal. So it is a combination of isentropic and isothermal processes. Now I will draw some diagram which is called as the PV and TS diagram for Carnot cycle. So here we have PV, that is pressure and volume, and TS, temperature entropy diagram for Carnot cycle. So now while I am drawing the diagram, this diagram is nothing but a graph of pressure versus volume and temperature versus entropy, that is PV and TS diagram. Now I'll look at the first process. The first process is reversible adiabatic compression, that is isentropic compression. So isentropic compression will be shown on PV diagram with the help of a curve. Now this curve which I have drawn, it will have two states, state 1 and state 2, and this curve indicates a compression process, because if we see volume at point number 1, that is V1, is greater than the volume at point number 2, that is V2. So V2 value is less, V1 is more. It means compression process has taken place, air has been brought inside the engine and then compressed. So its volume decreases and pressure increases, as we see here. Initially the pressure was P1, and after compression the pressure has gone up to P2. So volume decreases and pressure increases during the compression process. Now the second process is reversible isothermal heat addition. So isothermal line, again it is shown with the help of a curve here, as I have drawn this curve from 2 to 3. This indicates the heat addition process, and heat addition is isothermal, so we are getting a curve here. Next, process 3 to 4 is reversible adiabatic, that is isentropic expansion. So after the heat addition process there will be expansion process. So now process 2 to 3 is heat addition, and this is isothermal curve because the process is reversible isothermal heat addition. Next, after that, process 3 to 4 is reversible adiabatic, that is isentropic expansion. Previously we have seen isentropic compression, now expansion. So after point number 3, that is once the heat has been added, there will be expansion process. So like we had drawn it for the compression process, parallel to that we'll draw a curve for expansion process. So here this curve which I have drawn, that is 3 to 4, indicates expansion process. So when the heat was added up to point number 3, here the volume was V3 and after the expansion has taken place, volume has increased, because during expansion the volume increases and pressure drops. So here this graph or this curve is going down because volume should increase and pressure should drop. Next, the last process, which is reversible isothermal heat rejection. So once the expansion has taken place, now the heat would be rejected. So again the process is isothermal from 4 to 1, that is isothermal heat rejection. Next, similarly, as I have drawn the PV diagram, that is the pressure volume diagram, I'll draw the temperature entropy diagram. The first process is reversible isentropic compression. So on the TS diagram, entropy should remain constant because it is isentropic process. So here I'll denote this is process 1 to 2, and since the process is isentropic means entropy should remain constant. So if we see here, the entropy is S1 is equal to S2, entropy remains constant, and during compression process pressure increases and even the temperature increases. So here from 1 to 2 the temperature will go on increasing. Next, heat addition is from 2 to 3, and that was isothermal heat addition. So isothermal means temperature should remain constant. So here 2 to 3, here I am drawing a horizontal line which indicates constant temperature, that is T2 is equal to T3, isothermal heat addition. Then there is isentropic expansion from 3 to 4. Again the entropy will remain constant, and since it is expansion, temperature should drop. So here the temperature is dropping from 0.3 to 4. Entropy remains constant, that is S3 is equal to S4, and the temperature has dropped because in compression process temperature increases, but in expansion process temperature decreases. So this is isentropic expansion. Then 4 to 1, it is again isothermal heat rejection, that is temperature remains constant. So temperature at point 1 is equal to temperature at point 4, isothermal heat rejection. So now here on this PV and TS diagram, I'll mark that first of all during process 1 to 2, since it is a compression process and during compression work is done on the engine, or work is done we can say on the gases which are present inside. So here I'll show an arrow which goes inside the cycle, that is work is input, and this work would be denoted as W suffix C, that is work which is done on the gases or on air during compression. Next, after the isentropic compression process from 2 to 3 we had heat addition. So here heat is added, that is Q suffix A, heat added. Next, once the heat was added from 2 to 3, then from point number 3 the gases will start expanding and we will be getting work from the engine. So work is getting away, that is we are moving away from this cycle. So work, I'll denote it as W suffix E, that is work which we are getting during the expansion process. Now from 3 to 4 the work during expansion gets completed, and now from 4 to 1 the heat rejection starts, that is after the completion of work the air, or we can say air fuel mixture which is present inside the engine will be taken away from the engine. So that is heat rejection process. So here heat is removed or rejected from the system, so that is Q suffix R. The same thing I'll denote it here from 1 to 2 the work is done during compression. From 2 to 3, heat is added into the engine cylinder. Then 3 to 4, there is expansion, work has been developed by the engine, and from 4 to 1, there is heat rejection, that is the heat goes out of the engine. So here the Carnot cycle we have seen on PV and TS diagram. I'll write some important points here, that during compression process, because the first process is reversible isentropic compression, so during the compression process, air, as we are using air as a working medium for the air standard cycles or gas power cycles, in that the working medium assumed is air, so air is compressed, increasing its pressure and temperature by reducing its volume. So during the compression process, as we can see here in the diagram, air is compressed, increasing its pressure and temperature by reducing its volume. Next, after the compression process, heat is added, that is heat addition takes place, and the process is reversible isothermal process. So when the compression process has been done or completed, after that the heat addition starts. So here, as we can see, at point number 2 the compression is completed, and after that the heat addition starts from 2 to 3. As we can see on both PV as well as on TS diagram, the heat addition starts after the compression and it ends on point number 3, and the process is reversible isothermal. Next, after the expansion, or we can say after the heat addition has been completed, after the heat addition process, expansion of air takes place, thereby producing work output, that is W suffix E, work which is produced during the expansion process. So now, as I have written the fourth point, that after getting the work output, that is W suffix E, from the engine, the air should be, or the air should reject the heat from the engine, and that heat rejection is at constant temperature, that is isothermal heat rejection. So for that, I'll explain it with the help of a diagram, that how a Carnot engine looks like. Here I am drawing the diagram for the Carnot engine. These are the cylinder walls, and this is the cylinder head. Now, this is the cylinder wall, and here we have cylinder head. Cylinder wall in case of Carnot engine is a perfect insulator, whereas the cylinder head is a perfect conductor. So, this is the diagram of the Carnot engine. So here, when we have air inside the Carnot engine, and that air will be compressed with the help of a piston. Here I have not shown that piston. So when the piston is compressing the air, suppose here the piston is there. Now, when this piston would be compressing the air, after the compression, as we know, there is heat addition process. So since the cylinder head is made a perfect conductor, at that time the heat source would be brought close to the cylinder head. That is, the heat source, here we have the heat source which will be at high temperature. That heat source will be giving heat to the air inside the engine through the perfect conductor, and this is the heat addition process taking place inside the Carnot engine. Next, once the heat has been added, the heat source would be removed, and then there will be expansion, that is piston will be moving behind and we will be getting the work output. Now after the work output has been reached, we need to remove, or we need to reject the heat which is there inside the engine. So for that purpose we have another reservoir like heat source. There is a reservoir called as heat sink. Now that heat sink which is at low temperature will be brought close to the cylinder head, and the heat which is there inside the air, that heat will get transferred to the heat sink, because heat sink has low temperature, and here in this way the heat rejection process, that is QR, takes place. So this is the diagram of a Carnot engine, and because the walls are perfectly insulated, the heat transfer is zero. Heat transfer is 0 through the valve, that is Q value is 0. Only heat transfer which takes place, that takes place through the head of the cylinder. Next, as we have seen, there is Carnot engine. Now I'll write down the efficiency formula. Therefore, efficiency of Carnot engine is given by efficiency of Carnot engine is, it is maximum temperature minus minimum temperature upon maximum temperature. So here we have written the formula of Carnot efficiency. It has maximum temperature, maximum minus minimum upon the maximum temperature. Now let me write down some of the limitations of Carnot cycle. Limitations of Carnot cycle. The first one is Carnot cycle is not restricted by the type of fuel. Carnot cycle does not take into account the kind of fuel used. Means we can use Carnot cycle everywhere because the fuel is not mentioned specifically. Then as we see that in the processes which we have seen, process 1 to 2 was reversible isentropic process, that is reversible isentropic compression. 3 to 4 reversible isentropic expansion. So both the processes are isentropic, that is heat transfer is 0, and for that purpose if we want an engine such that the heat transfer is 0, we should not give the time for the working medium, that is air, to exchange heat. It means the piston in the engine should move very fast so that there is no heat transfer. So I'll write down that for reversible adiabatic processes, that is both compression as well as expansion processes, piston should move at a very high speed so that there is no time for air to exchange heat, so that the heat transfer process is 0. The piston should move at a very high speed. So now here as I have written that for the reversible adiabatic processes, that is both reversible adiabatic compression and reversible adiabatic expansion, piston should move at a very high speed so that there is no time for the air to exchange heat with the surroundings. Then for isothermal processes, that is isothermal heat addition and isothermal heat rejection, piston should move at a very low speed so that temperature cannot change quickly. So during the isothermal processes, piston should move really slowly, that is the piston should move slowly so that there is no sudden change in temperature. And previously we have seen for isentropic compression and expansion, the piston should move really fast so that there is no heat transfer. Next, here I'll write down that hence to make such an engine in which the piston speed increases suddenly during compression and expansion, and piston speed reduces, that is piston moves very slowly during heat addition and heat rejection processes. So hence to make such an engine in which the piston speed increases suddenly during compression and expansion process and piston speed reduces, that is piston moves very slow during heat addition and heat rejection processes. So in two processes the piston moves at a very fast speed, and for the remaining two processes it moves at really slow speed. So hence to make such an engine is impossible. So this is the limitation of Carnot engine, that it is not an actual engine, or this cycle is not an actual cycle. It is only a theoretical concept. Then we can say that to attain reversible processes in actual is extremely difficult. So that is why Carnot cycle is not an actual cycle. And I can say that hence for all the above reasons, Carnot cycle is not a practical cycle. The Carnot cycle is not a practical cycle, and for that I have given some of the reasons, and with this we complete the description regarding Carnot cycle.